Next problem is from chapter 25. This is number 42. So this one says that we have four 1-gram spheres, that would be the mass. They're shown in the figure. They are released simultaneously and allowed to move away from each other. What is the speed of each sphere when they are very far apart? So these charges are going to separate from each other. From the symmetry of the situation, notice that all the charges are the same. They are at the corners of a square, so all the distances are the same. So you expect those charges to move along those diagonals of the square, and they're going to repel each other. And when they are far, they will pick up some speed as they're moving. So when they're very far away, what's the speed that they have? That's the question. So notice that we're starting with the charges at rest. This might not be said explicitly here, but there's no other way to solve this problem. So the problem says that they're allowed to move away from each other, which means that before you allowed them to move, they were not moving. So just simple logic tells you that in this problem, the charges are starting from rest. Then as we let them go, they're going to be repelling each other. So there's going to be an electrical force that is responsible for pushing these charges away. And that force is going to do some work because the charges move as a result of this force. And the spheres, because of this work done on them, they're going to speed up. And we're looking for the final speed when they are very far away. All right, so notice that the spheres move because of the electric force. Is the only force in this problem is the electric force. No other force has been mentioned here. So when we're dealing with these electrical or problems with charges, we're going to assume that there is no gravity unless the problem explicitly mentions gravity. So the only force acting on these charges is the electrical force, which we know it's a conservative force. This was discussed in this chapter. So conservative forces, guess what? They conserve mechanical energy. So we're going to use conservation of mechanical energy in this problem to solve it. If you can use conservation of mechanical energy, you should go ahead and use conservation of mechanical energy. So the conservation of mechanical energy says that the initial mechanical energy is going to be equal to the final mechanical energy. In the initial situation, the charges are at rest, sitting there at the locations indicated in the picture. So they're not moving, so zero kinetic energy at the beginning, but they do have electric potential energy because they're charged and they're close to each other. So the initial energy is simply going to be, because there's no kinetic energy, it's just going to be the amount of electric potential energy. So what is the electric potential energy of a group of charges? Again, this was obviously discussed in one or more videos in your homework, etc. You should know what we're talking about here. So the electric potential energy of a group of charges is the sum of the electric potential energy of all the interactions of the system. That is, you're adding the potential energy of all the possible pairs that you can form out of the charges in the system. The notation, this is usually written like that with an I less than J, and that just means you're adding over all the pairs the terms K, Qi, Qj over Rij. So I'm going to call the charges 1, 2, 3, and 4, moving counterclockwise from the top right. And the first interaction is going to be the interaction between charge 1 and 2. That's going to give us one term in that summation. That's going to give us one term. We're going to have the interaction between 1 and 3. The interaction between 1 and 4 gives us another pair. The interaction between 2 and 3, 2 and 4, and finally 3 and 4. These are all the different pairs that you can form out of 4 charges. So notice that the potential energy then is going to have 6 terms. I drew 6 lines there, so there's going to be 6 terms in that summation. 4 of those terms are identical. They're all the same because all the charges are equal, and the distance A, the length of the side of the square is, I'm going to call it A. We're going to replace it in a minute, but I just want to call it A for now. So we got 4 terms that are of the form K Q squared over A, and then we have 2 more which corresponds to the diagonal the interactions of the charges located in opposite sides of the diagonal. So that interaction has a potential energy of k q squared divided by the distance. What's the distance between the charges on opposite sides of the diagonal? The distance is the length of the diagonal, and the length of the diagonal of a square is the square root of 2 times a. Hopefully you can figure that out using Pythagoras. So we have two pairs of interacting particles across the diagonal. So those are the total of, so that adds up to the 6 terms that we were talking about. 6 terms that we need to add to get the total electric potential energy. So we can pull out something here just to do a little bit of algebra before we replace all the numbers. Both terms have kq squared over a, and first term gives you 4, the second one gives you 2 divided by the square root of 2. Plug in the numbers for that term. The 4 plus 2 over square root of 2 gives you 5.41, and then kq squared over a. I'm going to put in the numbers now, no need to keep it symbolic. So 5.41 times k is 9 times 10 to the 9. Q, the charge, one of the charges is, or they're all the same, so it's 10 times 10 to the minus 9 because it's 10 nanocoulombs. And don't forget to square it. And the distance between those charges, the distance or the length of the side of the square is, I'll call it a in the picture. That distance is 1 centimeter, which is 10 to the minus 2 meters. So that's the numbers that you plug in your calculator, and you get 48.7 times 10 to the minus 5 joules. Again, I was careful with writing all these numbers in MKS units, so I can be sure that the answer is going to be in joules. So 48.7 times 10 to the minus 5 joules is the initial energy of the system. Now, the equation that we want to use now is that the initial energy equals the final energy, just like we do in conservation of energy problems. Initial energy equals final energy. What's the final energy? Well, the final energy has kinetic and potential. The potential energy of these particles, what is the final moment? The final moment is when they have moved very, very far from each other. So at that time, when they're really far from each other, the potential energy should be 0, because the potential energy involves the distance between the pairs. So if they are very far away, the r in the denominator is a very, 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 very large number. Therefore, you can approximate that to 0. The electric potential energy when the charges are far away is 0. But they still have kinetic energy. They cannot have just 0 kinetic energy or the energy would have been lost. The initial energy would have been lost. So they're very far apart, so the potential energy is 0, but the kinetic energy is not 0. The kinetic energy of the system is, well, you have 4 charges. Each one has a mass m, so the kinetic energy and the same velocity, we assume, because the charges are equal. The geometry is all the same. So the kinetic energy is 4 times the kinetic energy of one charge. And the kinetic energy of one of these charges when they reach infinity is mv final squared divided by 2. 1/2 of the mass times the velocity squared. Hopefully you remember that. So the kinetic energy, the final kinetic energy is 4 divided by 2 is, well, let me just put, so the left hand side we said the initial energy is equal to the final energy. The final energy is going to be just kinetic final. What's the initial energy? We have the number from the bottom is 48.7 times 10 to the minus 5, which I'm going to write as 4.87 times 10 to the minus 4. And that should be equal to the final energy, which is just kinetic. So the kinetic energy is 4 divided by 2 is 2 times the mass, which is 1 gram. So in kilograms, it will be 10 to the minus 3 kilograms. And the final velocity squared. So solving for final velocity, we get 2.435 times 10 to the minus 1. Just putting the numbers in the calculator and take the square root of that to get the final answer, which is that these particles at infinity, or when they're really far away from each other, they will be moving with a speed of 0.49 meters per second. All right, next problem. This is chapter 26, problem number 5. It's giving you, as you can see in the picture, it's giving you a graph of equipotentials in some region of space. It's labeled 0 volts, 10 volts, 20, 30, 40 volts. The equipotentials look like straight lines. And it's asking you to estimate the electric field E1 and E2 at the points indicated, point 1 and point 2. And don't forget that the electric field is a vector. So they want your answer as a vector. E1, answer for E1 should be a vector. All right, so how do we tackle this? So we have information about the electric potential, and we're looking for the electric field. So electric potential and electric field are related to each other. This is the topic of a whole chapter in your book. Chapter 26 deals with what do you do when you have information about the electric potential of a system or some region of space and you're looking for the electric field. You can also go the other way around. If you have information about the electric field, how do you get the information about the electric potential? So in this problem, we're going from information about the potential towards information about the electric field. So things to remember: relationship between electric field and electric potential. Things to remember, one of the important ones is that the electric field always points from regions in space with high voltage towards regions of space with low voltage. The electric field will always be flowing from high potential towards low potential. Like I said it probably in one of the videos, just like a river flows from high ground to low ground, the electric field flows from high potential to low potential. So that's important to remember here when we draw the electric field vector, which we're going to do in a minute. The other important information, a relationship between the electric field and the electric potential, is that the electric field vector always points or is always perpendicular at any given point in space. The electric field will always be perpendicular to the equipotential that passes through that point. So these two pieces of information tells us that the electric field at point 1 must be pointing straight to the left. Notice that we're assuming here that the equipotential that is going through point number 1, so point number 1 in space must have an equipotential at that point, right? So we're assuming that this equipotential would have the same shape as the neighboring equipotentials. So since they're all vertical lines, it's natural to assume that the equipotential that goes through point number 1, which I'm drawing with those dots, that equipotential would be a vertical line, which means that the electric field we should draw it at that point, we should draw it perpendicular or horizontal in this case. A perpendicular to a vertical line is a horizontal line. We could have drawn it to the right. Horizontal could be pointing to the right or pointing to the left, but we chose to draw it pointing to the left because the electric field always points from high points in potential towards low points in potential. Notice that the high potential is to the right and the low potential is to the left. So the electric field must point from right to left. So this gives us the direction of the electric field at point 1. We don't know the magnitude, but we're going to do that in a minute. So again, notice that it must point from high potential to low potential. All right, for point 2, we're going to do the same thing. We apply the same two rules. So the equipotential that passes through point 2, the 30 volts equipotential, it's a vertical line, so the electric field must be perpendicular to that line, so it must be horizontal, and it should go from right to left because the high potential is 40 and the low potential is 20, so it must be going from right to left. So this is the electric field at point 2. That's what the vector should look like. What is the magnitude? How do we estimate the magnitude of the electric field? So we're going to estimate, that's why this symbol means estimate or approximate value, this symbol right here. this one here. So we're approximating the magnitude of the electric field by using the equation, by taking the absolute value of delta V over delta X. This delta V is going to mean the difference in the electric potential evaluated at 2 points, to the right and to the left of the point of interest, divided by the distance between those 2 points that we selected. This equation came from, or is the approximate version of the exact equation, which is the electric field in the x direction is the derivative with respect to x of the electric potential. So the same thing applies for the y component of the electric field. We do know in this problem that there is no y component. We're expecting the electric field to be fully horizontal because it should be perpendicular to the equipotentials. And we can take a derivative because we don't have the function potential as a function of x at all points in space. So that's why we're going to have to do this approximate calculation. And in this approximate calculation, we're going to look at 2 points, one to the right and one to the left of the point of interest. What's the point of interest? Where they ask us to calculate the electric field. So we look at a value of the electric potential to the right and to the left of the point of interest. So to the right we have 10 volts, to the left we have 0 volts. So 10 minus 0 is the delta V that goes in the numerator. In the denominator we have the location where we found the 10 volts, that's indicated by 2 meters, minus the location of the point where we have the 0 volts. So 10 minus 0 divided by 2 minus 0, and that gives us 5 volts per meter. So that's the magnitude of the electric field, E1. In vector notation, we can write E1 as minus 5 volts per meter times I hat. That tells us the direction and magnitude of the electric field, E1. Moving on to the calculation of the electric field at point 2, we're going to use the same approximate equation. Again, we're going to look at a point to the right and to the left. So to the right we have 40 volts, to the left we have 20 volts. So the point on the right, that is on the 40 volt equipotential, has a location of 4 meters. We're going to subtract the location of the point on the left on the 20 volt equipotential, so that's 3 meters. And the numerator gives us 20 volts, the denominator gives 1 meter. So the magnitude is 20 volts per meter for E2. And the full vector can be written as minus 20 volts per meter I hat. Again, minus because it's pointing to the left. All right, those are the two answers for the approximate value of the electric field at point 1 and 2. One thing to notice here is that the electric field E2 is stronger than the electric field E1. It's in magnitude 20, whereas E1 is 5. Notice that is related to the fact that the equipotentials are closer together at near the point 2 than near point 1. Notice how in the neighborhood of point 1, the two equipotentials have a difference in voltage of 10 volts, but that difference of 10 volts happens over a distance of 2 meters. Whereas for the equipotentials near point 2, we have 10 volts, but over a distance of what looks like half a meter. So the closer the equipotentials are, the stronger the electric field in that region of space.